Okay, odd even jump 975. You're given an integer array A from some starting index. You can make a series of jumps. The first, third, fifth jump in the series are called odd number jumps, and the second, fourth, sixth jumps in the series are called even number jumps. You may, oh man, I'm getting the sniffles. You may from index I jump forward to index J with I less than J in the following way. You can jump forward, okay. During odd number jumps, 1, 3, 5, you jump to the index J such that a sub I is less than or equal to a sub J, and a sub J is the smallest possible value. If there are multiple such index J's, you can jump to the smallest such index. There's a lot of reading in this one. Give me a second. During even numbered jumps, you jump to the J such that a sub I is greater than a sub J, and a sub J is the largest possible value. If there are multiple such index J's, you can jump to the smallest such index J. It may be the case that for some index I, there are no legal jumps. Starting index is good. If starting from that index, you could reach the end of the way by jumping some number of times, possibly zero or more than once. Return the number of good starting indexes. Yeah, I mean, my first intuition is just that this is a breadth first search. But let's take a look at the kind of the constraint first. So 20,000 numbers. So yeah, breadth first search is probably right, but or some kind of shortest path type, or like single source. What's it called? Yeah, but one of the shortest path where you have a single source that goes through all the other ones. But I think I have to really read this problem again because it's just very confusing, to be honest. Well, it's not that confusing, but it's a little late and I'm a little tired and I'm just trying to make sure that I understand this correctly. Okay, for example, there's an input that's 10, 13, 12, 14, 15. From 0, we could jump to use 2 because A sub 2. Okay. So I guess there's always one at least, but that's besides the point. Okay, so for each of these, for example, the 10 will go to the smallest number to the right of it. Okay, and that's for the odd number ones. But the even number ones, it will take the largest value from over there. Yeah, where and you take the smallest such index, so the one to the leftmost, but the highest. So why can't 13 go to 13 goes to largest possible. Oh wait, this is an even number jump, odd number jump side. That's why. Okay, so 13 will go to the 14 because it's the smallest number that's larger than 13. Okay. Okay, so with these kind of graph problems, I think the in theory, I mean, there are different ways to model it, and this is definitely a graph E problem, but that's only one component of the problem. There are other components as well, and some of them requires more advanced data structures. So I think the first kind of yeah. Man, yeah, sorry. Yeah, so the first part is, yeah, constructing kind of the graph. And either implicitly or explicitly. But because of length is 20,000, you can't really create like an n squared graph or have an n squared way of doing it. But for 20,000, I think I would try to find something that's n log n, I guess. Probably one in time. Yeah. So maybe this is the binary search one that we were thinking of, but to the smallest possible value. That's and each element could be up to 100,000. Okay. So I think the core. So and also like this is even though I said it is a graph problem for the most part. No, each index has only or each node which has a one-to-one correspondence with the index can only have one out edge, and constructing the graph is kind of the hard part of the problem, and then after that it's just a connectivity thing. I mean, I might have said, I mean, I've definitely said shortest path, but you don't actually have to return the path. You just have to. It's more of a reachability, right? So you still use breadth first search or something similar. Well, probably breadth first search, but the actual problem is about constructing the graph, and yeah, and for this problem, you're just trying to figure out. Yeah, you're trying to create the data structure such that, well, you're solving two problems. One is that for odd indexes, yeah, for odd, wait, man, this is actually, man, this problem was also a little confusing because I think the odd numbered jumps is actually the even numbered index, and the other way around. So I am very kind of annoyed by that. But 13 jumps to what? Wait, is that true? Because okay, so I don't understand this explanation. That's what I'm trying to read right now. For example, for 13, we can jump to I equals 3. Why? 1, 2, 3. So 13 can jump to 14. But why can 13 jump to 14 if it is? Because it's not. I think I conflated some stuff, but that's fine. But basically, what you would actually do is you just double the number of nodes, one for each odd number jump and each and even numbers, and just see if you could get to either of the n. But yeah, so that's. I mean, it's still the same problem. You still have to solve all this things, but how to do it. So, and you have to do it faster than n squared time. Uh, so, okay. I think this is maybe similar than to the last one we've done. Maybe can we? Okay, so for each index, we have to figure out, we have to solve both of these, or not solve, but we have to figure out the smallest number that's bigger than this number. Um, but not like, yeah, I mean, I think that's not that bad. I mean, you just kind of sort it, right? Yeah. Okay. Yeah, so you just, I think you just, I was trying to think if there's anything tricky that I have to do, but if you just sort it and then you just create edges to the stuff adjacent to it, I think that should be good. Yeah, okay. Uh, yeah, I mean, and also for the other one. So let's create two arrays. One is smallest, larger. So basically, it's the smallest number that's larger than this current number is equal to a list, and it's equal to something like that, right? I mean, hold on a second, but let's see. Yeah, okay, well, oh, whoops. Printed even the wrong one, so that didn't help. Okay, so it is sorted, but let's see. Does this work? Oops. Oh, well, I mean, it kind of works, but but my laptop is just screwy right now. But it kind of works, but we actually want to flip the way. Okay, fine. Let me just create an alternate thing. Um, or I could just pass in a function. How do I pass? I think it's like lambda, right? Okay. Maybe something like that. It's been a while. Okay, wow, that actually surprisingly worked really quickly. Okay, but yeah, now you have this array, and that actually is just sorted in it. Actually, the naming is not even matter. Okay, so now all we have to do is kind of create edges so that we can get to them easier. Oh, Jesus. And now what I said about graphs, actually, I think because each point only has one out graph, we actually don't even need to, we could just walk the DAG with some kind of, with some memorization so that, so we don't do the same thing twice. But that should be good. Okay. Well, that works for the smallest, largest, but is that true? Well, no. I mean, this worked for the first element, and the 212. Well, that's not going to work. But actually, and this is kind of very coincidental. But now we do the thing where again with the stack, right? So like here we put this on the stack, the first element, and then let me just type this. So we put the first element on the stack. So the stack is 0, 10, and then when we get to 212, we pop this off. And then when we process 113, well, we can't. So we just push this under the stack. And then now we do 314, and then now we pop these two, right? Okay, yeah, so that's how you would construct them again. Okay, so now it's very coincidental because again we solved the same problem twice in a weird way. But okay, let's do odd numbered jumps for now. Times ln of a, and then now okay, so okay, literally did this earlier today, so the same idea here. So it's index bigger than x. No, you care about index. If the index is bigger than your current index, then you pop, right? Because I don't actually even need this, but oh man, I was hoping at least something came out. But okay. Oh, whoops. I guess it should be on the. So just need to enumerate now. Oh, this works for one element. But why doesn't 12? Maybe I got to. Oh, yeah, that's right. So on odd number jumps, 0 will go to 12, 13 will go to 14, 12 will go to 14, and 14 will go to 15. So this is working as expected. And then now we have to do the same thing with the even number jumps, except for in reverse. Let's see, which one is it again? So the largest number that's smaller than this number. Okay. Largest number that's smaller than this number. I mean, it's probably something similar, but. So actually, now we want the reverse of this. Yep, okay, so that's largest number that's smaller than this. That's good except for the, wait, is it? Yeah, it's good. It's just that in this example, the very few even number jumps. Yeah, just that this example may not have even number jumps. Let me see if we try this second example. So. In this case, 0 will go to 2, but that won't happen on even numbers. Okay, so I think this is right, maybe. Even number. A lot of stuff that could have been copy pasted, I guess. But so an even number, 2 can go to 1, which is probably true. 3 can go to 1. 1 will go to 3. Oh, yeah, go to 3, and then that's it. Okay, so that seems right. And now I think what's left is just kind of I mean, we said something about breadth of search earlier about finding connectivity, but given that we kind of construct this graph in this way, I think so. There are 2 ways you can do about it. One is kind of go backwards in time, or like create the inverse graph of the even number jumps and the odd number jumps, or you can just kind of, what I'm going to do is I'm just going to go forward and do a recursive thing with memorization. So let's do it. I think there's a memorize function too, but I'm not going to use it because not familiar. I mean, I know of it, but I'm not super familiar with it. So maybe there's some homework for me next time. But X in A. So now we will it's possible. Let's make it odd just so that it's easy to remember. I guess we have to pass A. Yeah, okay. Oh, well, we have to pass all the other stuff that we calculated. Cool. Okay. Okay, why don't I just make it a Boolean? Then the current index return is possible. Well, I'll do the base case in a second, but number jumps index. I guess I could just choose force. I could make this less wordy in a second. Hang on. So that's roughly right, but there's going to be some if conditions and stuff like that. So I just do like Mm. Oops, did that twice. So now we just return. Okay, now base cases. Well, if index is equal to what is it? None of a -1 maybe, then return true, right? That's mostly it, really. Oh yeah, and we have to check to see if fourth. Okay. Well, let's quickly run this through. I think there's some memorization that we can do here to make sure that it doesn't spiral into some craziness. I mean, not craziness. It would just be a, oops, said a, but n square, which that's for 20,000 is not what you want, but otherwise it should be okay. Can I do this? Also, I misspelled it. I have too many windows open. Oh man, what is that library called? Font tools. Yeah, okay, fine. I'll just manually do it. It's been a while. Okay. If whoops. Try another example. Did I try that one? Not sure I did. No. Try the first one. Now let's try some empty cases and stuff like that. I mean, I think in theory I would also try a big case, but I'm kind of lazy right now. Ooh. Oh no, that's the expected. So I kind of got that right, but I don't know. Well, I mean, I think I got it right more than they did anyway. I just want something big-ish, just to make sure that it works. But okay, wow, that was very quick. But okay, that's just submitted then. Hopefully I don't have any edge cases. Cool. Okay, so this was accepted. Man, one time pretty slow. But okay, yeah, so for this one, I think we're at the same. I mean, it's a little unfortunate in the sense that we have a duplicate idea of what we did last time. But I think as a result of kind of these extra complexity, this is actually a problem that I like a lot. As an interview, I think it would have probably taken me a little bit longer to figure it out if it weren't for that, obviously. But I think as an interview, I would actually like this problem just because it, like again, all these are kind of very basic concepts. There's the stack. Also, as an interviewee, I would probably make comment about modularizing this and cleaning this code up a little bit. Maybe kind of don't repeat myself a little bit. There's definitely some minor changes with that we can kind of fix. Actually, I think the only thing that's different between these two things is the lambda functions here. So we can definitely dry ourselves by putting it into two different arrays that way. So that's actually a very easy code cleanup. But as an interviewer, I like having layers, and I like kind of seeing things this way. There's graph, there's stack, there's a little bit of memorization, though it's not super necessary if you had done it the other way with breadth search from the end. But still, like there are a couple of steps, and it takes kind of linking them together, and that's what I like about it as an interviewer. I think this is possibly a little bit on the hard side, to be honest, in an interview, but it's also one of those things where I would not necessarily ask the interviewee to have an optimal answer. I would just kind of ask them to work through it and ask them to, halfway through or whatever, have the time to actually write some code so that we can kind of see where it goes. But otherwise, I could see myself using this question as an interviewer. Maybe it's a little tricky, but I think there may be a little bit of calibration that we can kind of do, and maybe maybe take out the odd even thing. But for the most part, I think this is a fun problem, and yeah, I mean, I think that it takes a little bit of understanding, but otherwise, I dig this problem, and I would like to maybe play around with to get the calibration right on an interview.